Okay, hello everyone. Today's origin seminar speaker is Yue Hu from University of Wisconsin Madison. He's in physics department and is graduate student, fifth year graduate student working with Alex Lazarian, and he's an enthusiast of magnetic field. So we'll hear about characterizing three-dimensional magnetic field in star-formed regions. So, yeah, the floor is yours.
Oh, hello everyone. Yeah, thanks for, first I would like to thanks for Selena and also the organizers for inviting me to give that seminar. And I'm going to talk about two new methods to trace three-dimensional magnetic field in star-forming regions. And first, I would like to begin some basic introductions about the new method and what is magnetic field and turbulence in astrophysics. And turbulence and the magnetic field actually are very ubiquitous and pervasive in our universe. They are important in galaxy clusters that were large-scale structures in galaxy, and also that's very important in smaller scale like star formation in central molecular zone or that regulating cosmic rays. They are so important in many of the physical phenomena. And in my work, what I'm trying to do is to combine magnetic field and turbulence. Their effect to get a new view of a three-dimensional magnetic field. And the three-dimensional magnetic field, actually, I would like to focus on for today's talk. I would like to focus on star formation, because as you know, typically we have two models of star formation. One is strong magnetic field model, in which the gravity is mainly supported or against by magnetic force. And we also have a weak magnetic field model. In that weak magnetic field model, the gravity is against by emission turbulence pressures. But until now, we are not sure which model is more realistic or more accurate, because we don't have sufficient magnetic field information. And in order to answer this question, which model is more realistic, we need to have no magnetic field. And especially, it's not a two-dimensional magnetic field, but a three-dimensional magnetic field. Typically, with the magnetic field on the plane sky can be measured by polarization, the position on the plane sky XY plane. But we need to understand star formation, we also need to know what's the inclination angle, like the magnetic field inclined with respect to the plane of sky or the line of sight. And that's the three-dimensional orientation. And we also need to know the strength, the total strength of magnetic field. And in this case, we can know what's the full effect of the magnetic field. Otherwise, the picture is incomplete. And the three-dimensional magnetic field is necessary, but it's very challenging to trace in ISM or in star-forming regions. Like the cartoon shows here, suppose the elephant is a three-dimensional magnetic field. We have different methods to measure the magnetic field, like dot polarization, synchrotron polarization, powder rotation, or Zeeman splitting. But each of them is tracing different parts or different phases of the magnetic field. If we look at just the dot polarization, it will only give us the magnetic field on the plane sky and corresponds to cold gas phase. And like Zeeman splitting, we can only get the line of sight magnetic strength and in different multi-phase like H1, diffuse H1, or the dense OH molecular phase. So it's not easy to combine these three methods to get a single full three-dimensional magnetic field vector, because they're tracing different phases. And here I would like to introduce a new method to trace the three-dimensional magnetic field, rely only on dot polarization. And this new method will tell us not just the plane sky magnetic field, but also the inclination angle magnetic field, so we can recover the three-dimensional magnetic field orientation. So I would like to begin, let's see what's the basics of a dot polarization. So use polarization to trace magnetic field. The dot polarization is very simple because we have charged two dots that's rotating, essentially rotating in the direction perpendicular to the magnetic field. Such a preferential orientation ensures like the polarization orientation is perpendicular to the magnetic field orientation. Therefore, if we rotate the polarization angle by 90 degrees, we can get the magnetic field orientation. But this is on the two-dimensional magnetic field on the plane sky. So what about the inclination angle of the magnetic field with respect to the long side? If we have a close look at the Stokes parameter Q and U, we see such such information of inclination angle gamma is incorporated in the Stokes parameter. And if we assume a very toy model without any fluctuations and a homogeneous magnetic field, the Stokes parameter or the polarization actually can give us the information of inclination angle gamma. And P here, that's polarization friction, and P max is the maximal polarization friction. The ratio just tells us the cosine square of cosine gamma. But this is a very simple consideration. But in reality, we have turbulence, and we have the fluctuation of magnetic field. And from our numerical simulations, we can see here, if we have the magnetic fluctuation, which is characterized by MA, the polarization friction is also decreasing in the presence of the magnetic field fluctuation. It's not just a function of inclination angle gamma. Therefore, there's a degeneracy. We have the polarization friction is depending on fluctuation and also the inclination angle gamma. We need to solve or we need to model the fluctuation very carefully in order to solve the inclination gamma. That's what I'm going to do to model the inclination angle, to model the fluctuation part of the magnetic field. And here we are considering like the fluctuation is from the emission turbulence. So in this case, we need to mention some also the essentials of the turbulence. Hydro turbulence actually can be considered as isotropic eddies. The energy is injecting at large scales and cascading to small scales. But in the presence of magnetic field, we need to consider MHD turbulence. And in this case, the eddy is not isotropic, but anisotropic, and they are elongating along the magnetic field lines. Hopefully, internet. So is there any issues with the internet?
Yeah, it was a bit slow, but please go ahead. We'll let you know.
Okay, thank you. So the anisotropy means the eddy is not is elongating along the magnetic field line, and this anisotropy is widely observed in observation. Like here, I show an example in torus, and here the black segment is the magnetic field measured by starlight polarization. And we see apparent striations or elongation of structures along the magnetic field line. Then that's the anisotropy I talked about before. And why do we need to care about the anisotropy? Because if we consider the velocity fluctuations in two directions, parallel to the magnetic field and perpendicular to the magnetic field, we can find that the velocity fluctuation is more significant in the perpendicular direction. And here, like say that let's from numerical simulations, the perpendicular fluctuation is even 1 order of magnitude larger than the parallel magnetic fluctuation. They get converged at a large scale because we have isotropic driving of the magnetic field of its turbulence. Here, that's just a numerical effect. And here, that's a very important property. Like the fluctuation is more significant in the direction perpendicular to mean magnetic field. But this is for velocity fluctuation. What do we need is magnetic fluctuation. If we see just from, if we have a look at the induction equations, we can see the magnetic field fluctuation is proportional to the velocity fluctuation. In this case, we can also see that magnetic fluctuation is dominated like in the direction perpendicular to the mean magnetic field orientation. So that would be a major assumption in our method to model the fluctuation, that there are relative orientation with respect to the mean magnetic field. But here we also like to see the assumption with the presence of mean magnetic field assumes like the cloud, a star-forming cloud, has very strong magnetic field. It should be sub-alpha-unique, which means the alpha Mach number MA is smaller than 1 instead of super-alpha-unique. But fortunately, from our recent view from Pat et al. 2022, this review showed that the majority of the star-forming cloud is actually sub-alpha-unique. Therefore, we all consider theoretical consideration or assumption that the presence of mean magnetic field and the magnetic field fluctuation is perpendicular to the mean field is solid and can hold for majority of the star-forming cloud. So with this assumption, we did some mathematical calculations here. That's the final expression we get. The mean the inclination angle gamma actually can be determined by two values of the that's P max and P off. P max is observed maximal polarization friction in a cloud, and P off is friction corresponds to the minimal dispersion of polarization angle. And I would like to illustrate these three values a little more. Suppose we have a polarization friction map, and we also have a map of polarization angle dispersion. So what do we need is to find a position in which the dispersion is minimal. In this position, the turbulence effect is also minimal. Then we find the corresponding polarization friction in this position, and also the maximal polarization friction in this cloud. And their ratio will give us the inclination angle for this cloud. So that is how can we implement this method to trace a three-dimensional magnetic field in a star-forming cloud. And we showed here, we did a numerical experiment, like how can we recover the three-dimensional magnetic field using this method. And here that's a supersonic, that's just a MHD turbulence simulation in supersonic condition and sub-harmonic conditions. And we can see the blue segment, that's the measured magnetic field from our new method. And the red segment, that's the real magnetic field in simulation. And we can see this new method actually recovered the three-dimensional magnetic field very well. But this is numerical result. And here in observation, we choose one low mass star-forming cloud of Euclid, and we're using like the Planck polarization to trace the magnetic field. The plot on the left shows the streamline, shows the plane sky magnetic field orientation revealed by Planck polarization. And using our new method, actually we can get also the distribution of the inclination angle. Combine the inclination angle and also the plane sky magnetic field, we can recover a three-dimensional view of the magnetic field in OP Euclid. But this is just for three-dimensional magnetic orientation. What is still missing is magnetic strength. And to measure the magnetic strength, here we rely on the Chandrasekhar-Fermi method. And this method also assumes like the magnetic distortion or deviation is erased by the fluctuation by turbulent motion, small-scale turbulent motion. So suppose we have a mean magnetic field, and if we see a very large distortion of magnetic of the magnetic field, then that means the magnetic field is relatively weak compared to turbulence. Otherwise, if the distortion is small, we have a relatively strong magnetic field. And from this method, we can calculate the plane sky magnetic field using the velocity dispersion, which is characterizing turbulence. And also we can we need the information of the magnetic angle dispersion. And this method will tell us what's the plane sky magnetic strength over the Euclid cloud. And here on the left is a plane sky magnetic strength map. But interestingly, we see in these very high density regions, the magnetic field strength is even smaller or weaker than the low intensity regions, which is not expected because in high density region, we have gas compression, probably also the gravitational collapse. In this region where the magnetic field should be stronger. But remember, this is only plane sky magnetic field strength. If we recover the total magnetic field strength rely on the inclination angle obtained from a new method, we can see actually in this very high density region, the magnetic field is indeed stronger. And for this in full cloud or Beer-Class cloud, the mean magnetic field total strength is around 135 microgauss. This is a little bit larger than the measurement from Zeeman splitting, although they are measuring different phases, but we can get some roughly comparison between the two. And from this estimation, it's stronger than the Zeeman measurement. And we expect the reason is like the Chandrasekhar-Fermi method or DAC estimation overestimate the magnetic strength. Because in this estimation, we selected like a sublog to calculate the angle dispersion. And such selection of a small log means we are calculating fluctuation at smaller scale L. But the velocity dispersion measured from line with the emission line, that's the fluctuation at the injection scale. So they are measuring in different scales, and if we assume Kolmogorov turbulence, the angle dispersion in this sublog is underestimated, and this underestimation will cause overestimation of plane sky magnetic strength. Therefore, we expect that's one of the reasons that our estimation is stronger than the Zeeman splitting. And to solve this issue of overestimation by Chandrasekhar-Fermi method, we also employ like a different method that's called differential measure analysis. So for this method, instead of calculating the velocity dispersion from line width, actually we are using the structure function and the velocity centroid map, that's momentum one map, to calculate the velocity fluctuation. And this calculation will ensure both the velocity fluctuation and the angle dispersion, they are in the same scales, like same small scale L. So we don't have such an underestimation for the dispersion, angle dispersion, and we can safely say we can safely say we have better constraint on the magnetic strength. And from this method, we find the total magnetic strength is like reduced by a factor of 2 is 70 microgauss. And this is more close to the Zeeman measurement. And combine like up to now, let's say we have total magnetic strength. We have also like three-dimensional magnetic orientation. Therefore, this new method combined with Chandrasekhar method or the differential measure analysis, we successfully recovered the three-dimensional magnetic vector, including both orientation and the total strength. Okay, so but that's not the end of the story, because like we know, polarization measurement is measuring everything along the left side. It contains contribution from foreground H1 and also contains like diffuse molecular topsil and dense tracers HNC, the contribution from them. They are integrated measurement, and we cannot separate the magnetic field in different volume density or in different spatial positions. And however, the Zeeman splitting by Crutcher at 2012 shows the magnetic field is actually well correlated with the volume density. When the volume density is larger than 10 to the power 3, then they have like to the magnetic strength increases significantly, and that's correlated to volume density. Therefore, that tells us actually we need, in order to fully understand like star formation or the molecular cloud, we actually need to separate the magnetic field in different volume density range. But that cannot be done by polarization, because that's, as I mentioned, it's an integrated measurement. So here I just would like to introduce a new method, like the velocity gradient technique. For this new technique, we can employ, like we can use 12CO, the emission line for 12CO, pulsating on H and C to trace the magnetic field. Therefore, we can separate the magnetic field in different spatial positions and also in different volume density range. So here, let me just introduce a little bit about the velocity gradient. The velocity gradient technique also uses anisotropy of anti-turbulence. Here we see like the cartoon that the illustrator shows here. If we have emission turbulence, the turbulent eddy is elongating along the magnetic field lines. And if we consider the eddy has perpendicular scale, that's perpendicular scale with respect to the magnetic field. And also it has parallel scale, the scale parallel to the magnetic field. And if we consider the anisotropy, that means the parallel scale is much larger than the perpendicular scale. And if we calculate the velocity gradient in this case, we can easily find the velocity gradient is dominated by the perpendicular component. And if that's dominated by perpendicular component, the velocity gradient is perpendicular to the magnetic field. Therefore, we can get the direction velocity gradient and rotate it by 90 degrees, we can still get the magnetic field orientation. So this is basic idea, how can we use velocity gradient to trace magnetic field. And here again, let's see, that's a plot we already see before. That's for torus. In observation, we see such anisotropy. And if we calculate the velocity gradient, presumably it will perpendicular to the magnetic field and perpendicular to the eddy. And such anisotropy is also widely observed in our numerical simulation. Here we can see apparent striations or elongating structures, that's velocity structure, along the mean magnetic field orientation direction. So we can say statistically we can use the velocity gradient to trace magnetic field. But remember here we are using numerical simulation and this is the velocity slide. And in observation, actually we don't have such pure velocity information. Non-trivial to get the velocity information in observation. So here we need to extract the velocity information from the double shifted emission line, which means the emission line means the real density structure in XYZ space is mapping to XY velocity space. And this mapping will distort the density structure significantly. And especially according to the theory by Lazarian and Lazarian and Paulson in 2000, when the channel width or the velocity resolution of the emission line is very small or very narrow, that's smaller than the velocity dispersion, the observed fluctuation or intensity structure in the emission line in a cube is dominated by velocity fluctuations. And I will illustrate this effect a little better using a simple numerical experiment. Here I use a constant density cube XYZ in XY space, that's in real space. And also that's constant density cube, but we also have a real to keep the turbulent velocity cube, and using these two cubes we generate a synthetic emission line. And remember here that the constant density field, therefore we don't have any real density structure in the simulation. So let's see what happens if we generating an emission line and sorry. Yes,
can you play again? Try to play again. It worked before.
Yeah. Okay.
Yeah, it's working.
Okay.
It's working now.
Okay. You can see from the red shadow area means the integrated velocity range to produce the channel map. And as you can see, when we are decreasing the integrated velocity range, a lot of intensity structure appears. And remember here, I'm using a constant density field. Therefore, these structures are not real. They are purely produced by the velocity field. And this structure are elongating along the magnetic field, mean magnetic field line. Therefore, this tells us actually if we have very narrow channel or very high velocity resolution of the observations, the observed structures will be dominated by velocity fluctuation, and we can use this information to calculate the velocity gradient. So this is how can we implement the velocity gradient technique in observation. But this is for constant density field. You might also wonder what if we, in reality, like we don't have such constant density field. We must have some contribution from the density. As we observed in torus, again, the density structures or the elongating structures is not necessarily parallel to the magnetic field. It could be perpendicular to the mean magnetic field direction. And this is for torus, and also this is also observed in our numerical simulation. The density structures could be perpendicular to the magnetic field. So how can the density effect change our consideration of the thin channel, using thin channel to calculate the velocity gradient? And again, let's play the same numerical simulation, but in this stage, I'm not using a constant density field, but a real density field. Therefore, you can see a density structure that's perpendicular to the mean magnetic field. And then now let's decrease the channel width and see what will happen. And initially, if the density, the integration velocity range is very thick or very large, the density field does not change. But again, if we have very narrow or very small velocity resolution, we can see that the perpendicular density structure disappears. What is left is just some smaller striations, such striations of the structure that's along the magnetic field. Therefore, you can see here from the simulation, the density effect is actually not a big deal. And we can remove that density contribution by decreasing the channel width. So, okay, now we address this issue of density contribution. And now we can safely say we can use the emission line like the 1213CO for torus, and to calculate the velocity gradient and to recover the three-dimensional, two-dimensional here, up to now it's two-dimensional, the magnetic field. And we see very good agreement from the result for velocity gradient and the characterization. And this also, like we demonstrated in the numerical simulation, even if we have some strong perpendicular density structures, we can still trace the magnetic field. But this is for two-dimensional magnetic field on the plane sky. What do we need is this three-dimensional magnetic field. And fortunately here, we also have a way to get the three-dimensional magnetic field, because we also, okay, here I need to also talk about the anisotropy again in the channel map. This is also several channel maps that's obtained from the emission lines that's from numerical simulation. But what do we find if we change the inclination angle gamma from a large value that's 90 degrees? 90 degrees means the magnetic field is perpendicular to the long side. And we can observe very significant or apparent anisotropy. But if we decrease the inclination angle to be 0 that's parallel to the downside, the anisotropy disappears. And we didn't see a clear correlation between the structures and the magnetic field. So that means actually the anisotropy is regulated by the inclination angle. But that's not the only factors, because that's just a projection effect. What we find is also the anisotropy is also regulated by the magnetic strength. Let's say MA. The MA, that's the ratio between the fluctuation of magnetic field over the mean magnetic strength. For the upper panel, we have a strong magnetic field that's a small MA, and we see apparent anisotropy. But if we decrease the magnetic strength, and that's for the bottom panel, the anisotropy is insignificant. So actually, there's two factors: the inclination angle and the magnetic strength controls the anisotropy observed in an emission line. Therefore, we can see the basic idea is if we have such a correlation between the anisotropy and also like to the inclination angle and MA, actually we can solve this. And this to solve for the inclination angle and MA, we need two measurements of anisotropy because we have two unknown variables, the magnetic strength MA and the inclination angle. And we need two measurements with an independent measurement of the anisotropy. And then we can solve these equations to get a three-dimensional magnetic field. And such two measurements is provided by like BT ratio. BT ratio is actually the ratio between the maximal velocity gradient orientation in the histogram velocity gradient orientation, and B is the minimal value of the histogram of velocity gradient orientation, and that ratio characterizes the polarization, characterizes the anisotropy. And also we introduce another quantity that's P, that's a pseudo polarization friction. And that's also a measurement for the anisotropy. Therefore, there's two independent measurements, like that's preliminary numerical result. The two independent measurements actually can provide sufficient information to solve for the MA and inclination angle. And we can get a three-dimensional magnetic field. But this is just our preliminary result and it's numerical study. Up to now, I don't have any like observational application for this method. So I will show you what I will show is still just two-dimensional magnetic field orientation of the plane sky obtained from the velocity gradient. And I would like to remind you like what's the advantage of velocity gradient compared to the polarization friction. The velocity gradient, if we use 12-0 or 30-0 or HNC, we can separate the magnetic field in different velocity and in different volume density range. And here we employ like this idea to the Vela molecular cloud, and we use 7 different tracers from 12-0, 13-0, 18-0, or to HNC. And for the plane sky magnetic field, we compare it with the polarization estimate from the spectroscopic polarization. And we can see again the velocity gradient could recover the two-dimensional magnetic field on the plane sky very well. But we can also get information of how the magnetic field varies or change from the ambient diffuse gas that's traced by top field to more dense core like the traced by the dense trace HNC. And I call this three-dimensional magnetic field tomograph on the molecular cloud. And that's with a big advantage of velocity gradient compared to polarization. We can get more information compared to polarization. And if you remember, like the crystal molecular cloud I talked about before, and here we also applied the velocity gradient to OPU crystal cloud. And interestingly, we applied to the H1 emission, which could trace the magnetic field in the foreground region, and also to the Planck to the 12-0, and also compared with Planck polarization. And our discovery is the magnetic field on the H1, that's foreground region, statistically agree with the one in the molecular cloud. And this agreement, you can see the red area, the red vector means a very good agreement. And it means actually the magnetic field is coherent in the molecular cloud, and also the background and the foreground. The variation is very small, and that's a new information that we get obtained from velocity gradient and has not been studied before. Okay, so here, so for molecular cloud, so what I talk about for is magnetic field and turbulence. But like in molecular cloud or star formation, another important factor is safe gravity. And how can safe gravity change the velocity gradient? And if they are very significant compared to turbulence. So here, let's see. if we have assume that we have a safe gravitating cloud, and we have magnetic field line that's penetrating the molecular cloud. And if the molecular cloud is safe gravitating or gravitational collapse, it will have inflows or accretion along the magnetic field line. And in the diffuse regions, as we talked about before, is dominated by the emission turbulence. So the velocity gradient will perpendicular to the magnetic field. But that's not the case if we have gravitational collapse, because the gravity, strong gravity, will drag everything into the collapsing center, including the velocity gradient. The velocity gradient in this case, in the gravitational collapse, will be dominated by the inflow of the accretion. So it will become parallel to the magnetic field. And this is also observed in our numerical simulation, like here, that's a very dense molecular core that's gravitational collapsing. And the magnetic field is dragged into the collapsing center, and also the velocity field. And such a change, actually the gravity effect is, if we have first strong gravitational collapse, it will change the velocity gradient's direction by 90 degrees from perpendicular to parallel to the magnetic field. And again, let's see what the numerical simulation can tell us. That's a star formation numerical simulations. If we don't have gravities, the velocity gradient orientation, that's the histogram velocity gradient orientation, is concentrated on a single values. But if we include the gravities in a later stage, that means we have a significant gravitational collapse. The histogram shifted also to the left, from central to the left and the right. That means the velocity gradient orientation is changed by 90 degrees. Therefore, if we observe such a change in observation, that's velocity gradients, that's from ambient to that's changed by 90 degrees, we can see this region is gravitational collapsing. So this is the gravity's effect on the orientation. Also, the gravity will also affect the velocity gradient amplitude. If we have no gravity and the amplitude of a velocity gradient is constrained by the turbulence properties that's correlated by the injection scale, the injection velocity, and the magnetic strength. And if we have gravity, actually, if we think about extreme case that gravity is infinitely strong, and the velocity gradient amplitude will also increase significantly, and it's not bounded. Like in our numerical simulation shows here, that's the amplitude for the velocity gradient. Without gravity, it's concentrated on certain areas, but the gravity will drag the velocity gradient amplitude to higher values. So that's the gravity's effect on velocity gradient. It will change the direction of velocity gradients by 90 degrees. It will increase the gradient's amplitude. And this change, actually, in observation, as I mentioned, it can be used to identify which region is gravitational collapsing. Like this is for the also nearby molecular cloud surface, G3 to G6 cloud. And here we use 13CO to calculate the velocity gradient and compare it with polarization. And we can see in the low intensity regions, we have some agreement of velocity gradient and polarization. But here in the very dense regions, the velocity gradient got to be perpendicular to the magnetic field infrared from polarization. And such perpendicular the orientation tells us this region actually is gravitational collapsing. And it's also can be like to demonstrate by the red shifted and the blue shifted line, because we see overlapped morphology of red shifted and blue shifted gas. They are overlapped on the central dense regions, which which is suggesting like the gravitational collapsing is isotropic gravitational collapsing, therefore it created such overlapped morphology. And also another information we can get from velocity gradient is certain theories usually tracing the volume density around 10 to the power 3. Therefore, we can know that the gravitational collapse has its effect on such volume density range. So this is also a very important advantage for the velocity gradient. It can be used to trace three-dimensional magnetic field and also to identify gravitational collapse. And for the final topic, I would like to talk about a different application that's to understand the formation of the supermassive black hole. And here the scale I'm talking about is not such small, but in a large scale that's around 10 parsec. And the issue is the supermassive black hole means very strong gravity, but it does not necessarily mean that all ambient orbiting gas can fall into the galactic center, because we need a way to remove the gas angular momentum so they can fall into the galactic center. And here the effect that's never been studied, that's from the magnetic field, and I call it magnetic field breaking effect. Because we need to have external force to remove to the angular momentum so that the gas can fall into the galactic center. Such a strong torque or external force actually can be provided by the magnetic field tension. And here, as I showed here, that's beautiful image for the galaxy NGC 1068. The magnetic field has very distorted significantly in the galactic center or from the spiral arm to the center. Such distortion of magnetic field will provide very strong magnetic field tension, and this tension will also provide strong torque to remove the angular momentum. And this is potential one mechanism that how can the orbiting gas in such large scale can fall into the galactic center. And in numerical simulation, actually for this effect, magnetic effect is also apparent. If we need to have this numerical simulation from Kim and James Stone at 2012, that's for barred galaxy. So if we need to have, let's say, with the magnetic field effect very significant, we should observe its direction is being changed significantly. For instance, it initially follows the spiral arm that's following the inflow direction, and then it encounters the shock and being changed by 90 degrees and falling into the galactic center. And such a change at this position will provide sufficient or strong magnetic torque to remove angular momentum. And in their numerical simulations, here they are also try to use different magnetic strengths. That for beta from infinite to 1, and the beta is characterizing the magnetic strength. If beta equals to infinite, that means we have no magnetic field. That's essentially a hydro simulation. And we can see actually in the presence of strong magnetic field for beta equals to 1, the mass inflow rate increases significantly, even in the order of 2 magnitude. That means the magnetic field is very important in removing gas angular momentum to feeding the galactic nuclei. But this is the study was focusing on numerical study and analytical study. In observations, this has never been observed such change because that's difficult. And the problem is for dark polarization and synchrotron emission, they are measuring, that's an integrated measurement. They are measuring everything along the side, like to contain the contribution from the molecular gas or the diffuse gas. We cannot separate the magnetic field directly associated with the fueling process. Therefore, we cannot, it's very challenging to study what's the magnetic effect in fueling the galactic nuclei in observation. And here again, we can use the velocity gradient to solve this issue. And the issue now, the problem now is the velocity field for the galaxy is not so simple. The total velocity gradient contains contribution for turbulence, like from the shear and or outflow velocities. But notice that the turbulent velocity gradient is scale dependent. Its amplitude increases at a smaller scale because it's proportional to L to the power 2 to our 3 minus 2 over 3. The amplitude increases at a smaller scale. But the velocity gradient is scale independent for shear velocity. Therefore, if we have very good high resolution observations for the galaxy, and we can have the dominance of turbulence at small scales. And here there's a recent study for the turbulence in our galaxy, and it shows the galaxy turbulence dominates at small scale, like smaller than 100 parsec. Therefore, if we have such high resolution observations like from VRA or ARM, and we can resolve the turbulence scale, that's 100 parsec, we can use their observations to trace magnetic field using velocity gradient. And also like note, the way our observation is tracing H1 emission and fast ARMA, that's tracing the CO or H alpha emission, and using them, actually we can get different the magnetic field associated different molecular gas, and we can separate the magnetic field directly associated with the fielding process. So I would be a little bit quicker here. I'm running out of the time, sorry. And here I would like to show the one example of the application for the Galaxy NGC 1097. And here we have 3 measurements from the velocity gradient, from Hawk plus, that's dust polarization, and from VRA, that's synchrotron polarization. And here for dust polarization, for this cloud, we zoom into from big scale to the smaller scale. And we can see for dust polarization, we have a significant radial component that's perpendicular to the inner bar, that's magnetic field perpendicular to the inner bar, and follow the dust lane. And we expect such radial magnetic field and parallel to the dust lane means we have fresh dust that is feeding the galactic nuclei. But interestingly is the magnetic field obtained from a velocity gradient during cell emission is perpendicular to the dust polarization, and they are discrete with each other. And that is not expected because CO is tracing cold gas, and the dust is also expected to trace like the cold gas or cold dust. So that this disagreement actually means the dust has higher temperature. They are not tracing the same spatial position as the CO emissions. And that is not observed in our Milky Way, but in the starburst galaxy. And more interesting is the velocity gradient measurement agree with the synchrotron measurement. But again, like the synchrotron measurement is tracing the gas in a warm and ionized phase. It's not expected for this agreement. So our explanation is like the star-forming regions in this galaxy is still actively generating cosmic rays, and the cosmic rays cooling time is relatively short. So the synchrotron measurement in this case is still dominated by the contribution in the galactic disk or in the star-forming region. Therefore, we see such agreement between the CO measurement and also the synchrotron measurement. And this is for the comparison for different methods, but again, what our purpose is to confirm the magnetic field's role in building the galactic nuclei. And here, if you remember the numerical simulation, what we need is a change of magnetic direction by 90 degrees or a significant change to provide enough sufficiently strong positive angular momentum. And such morphology or such a change of magnetic field is apparently observed in this galaxy in the velocity gradient measurement. In the ambient, we see its magnetic field orientation is following spiral arm, and then it gets changed by almost by 90 degrees and following the inner bar. And that's exactly what Kim and James Stone was seeing in the numerical simulation. And this confirms magnetic field is important in removing the angular momentum and filling the galactic nuclei. Okay, and that's all my talk, and thank you very much. I'm ready to take questions.
Goodness, thank you. Okay, is there any question? So I have a question before somebody else. So for the you showed some serpents and the example and the torus example of Ophiuchus, right?
Yeah.
So is that the turbulence? That's something that we can trace that gas, and then would that any signature be left over for stars? So would the stars follow, if they follow the similar velocity, which actually we see that like from three-dimensional kinematic analysis of Orion A, it follows very well with the gas kinematics. So the velocity dispersion there, would that, I mean, and then the orientation, would they follow the original, I mean, the magnetic field if the filaments or the self-forming clouds that stars are born with, they had it, would they stars follow?
So you mean the star's velocity field will?
Yeah. Once the stars form, after that, when we see the stars.
Yes, that's an interesting question, and I think we need to separate the age of a star. If that's a very young star,
yeah, like a million-year-old, for instance.
If that's a very young star, that will follow the turbulent velocity field. If that's the gravitational collapsing, and it will like to. It has memory of the turbulence field in its parent molecular cloud, and this is also been shown by like to some analyze for Orion A, as I mentioned, that the stars statistically also follows like the Kolmogorov scaling, so they also have the memory of the turbulent field in the molecular cloud. And if we can also like to separate the star's velocity field in the perpendicular direction and the parallel direction, we can also use the star's velocity field to trace magnetic field. But here, that point is like the gravity effect is not significant. Otherwise, it's maybe not be expected if the star velocity field will follow.
It's a very dense cloud. A dense cluster, maybe not. But if it's not that dense, then the magnetic field memory may last quite long. I'm just wondering.
Yeah, it may not. If that's very dense, like clusters, it may not have the memory of magnetic field. Right. But if that's diffuse and very young stars, I think it will have the memory.
Okay, we have another question, Andrew.
Yeah, very nice talk. Thanks.
Andrew, I can't hear you.
Can you hear me now? Can you hear me? I'm unmuted.
Yeah, can you hear Andrew?
Yeah, I can hear you.
Okay, good. Yes, so I was wondering, you were comparing the scales of turbulence and differential rotation, shear, and the plot just went by a little quickly. I couldn't quite identify the break at 100 parsecs.
Okay, here. Okay, you mean this plot?
Yeah.
Okay, here I just mean like actually for this plot, that's just the velocity spectrum for turbulence. So actually, it's not comparing with shear velocity, but here we can see like from at 100 parsec, it's still following like the Kolmogorov scaling. So that means if that's a shear velocity, we didn't expect it will be Kolmogorov turbulence, right? So if that's still following Kolmogorov scaling, we can see maybe it's probably that's turbulence is still dominated that scale. But here, if we also see some large scale, but that's a particular feature of arm H1, we didn't care about that because what do we care about is a molecular gas. So I think 100 parsec is a safe scale. But here we didn't do like numerical studies or observational comparison for these particular values. It can be different for different galaxies.
Okay, But I guess what should I take from the fact that the same slope continues to larger scales beyond 1,000 parsecs? Right?
Yeah, yeah.
So turbulence, and then if it's not, is the slope, then why is it that slope?
Yeah, you're right. But here, I mean, here, this is if to 1,000 parsec, this is a particular structure of features that's the arm H1 arm for our galaxy. So probably we may not have such feature in other galaxies. So we expect to use 100 parsec, not the 1,000.
I see. You're saying in this case it is turbulence to larger scales, but in general you don't expect that, or?
Yeah, we didn't expect in that.
Thanks.
And also, like for the H1 arm here, I say it's in my opinion that's not my work, but I may feel like the slope here is a little bit strange here. It's not quite well as conical scale.
Oh yeah, no, always difficult to
yeah.
Okay, so any other question? All right, so otherwise let's thank you again and see you next week.
Thank you so much.